We have our capacitors, our electrolytics, film caps, paper caps, and we now want to design the capacitance leakage tester. And how do we go about that? So let's start with the capacitor. This is the capacitor that we want to measure the leakage of. And now you need to apply a voltage across it. So first thing we do is connect that end to ground, the ground of our system. And all you need to do now is apply a V+, a positive voltage, which you can vary. Now, why do you need to vary it? Well, you need to adjust it slowly from 0, preferably, and start increasing it to measure the leakage current that goes through here, which you will measure with an ammeter. As you increase that voltage, if this capacitor is leaky, the current will increase. And if it is not leaky, if it's fine, that current, after the initial charge, which will draw some current, it should be 0. So what we're doing here is measuring the leakage current for the particular voltage that we're applying on there, which, as I said, we can vary. The other thing that's useful is if we know what voltage we're applying to the capacitor at any one time, and for that purpose, we put a voltmeter across there. So as we increase the voltage here, we can see what voltage we are applying across the capacitor, and that serves two purposes. One, it tells us what the leakage is at a particular voltage, but it also helps us to increase the voltage to the actual voltage across the cap that we want. All we need to do is create a varying V+, positive voltage. And now this positive voltage should go quite high. How high? Well, if you're measuring capacitors that are rated for 1000 volts, you should be able to get 1000 volts. Do we need to measure for 1000 volts? Not in my case. I'm building this particular tester to measure leakages in capacitors coming out of old tube radios. And usually the highest voltage you get in these tube radios is in the order of 300 volts or so. So if I can get 300, 350 volts, I'm happy. I don't need to go any further. It helps me in various ways. One, in the transformer that I need to use. Two, in the type of circuit that I need to apply to create this variable voltage. And also, it makes it safer to work with, because the higher the voltages you are creating here, the more dangerous the entire circuit will be to use. So we need to design this varying V+, and basically what we need to do is create a variable high voltage power supply, which could be quite complex, and it could be very expensive. What I did was I went for the most expensive component of this system, which is the transformer, and I chose one that I had on hand. Let me show you. This little transformer was actually purchased for a tube preamp project that never got done. It delivers 240 volts out for a 240 volts in, or 120 volts in. So it's got two primaries which are wound in series, so 120, 120. I'm using it as 240. It then has one secondary output at 240 volts. This thing is rated for 30 milliamps, which is more than enough for my needs. And it also has a 6.3 volt heater output rated at 1 amp. So this guy is actually perfect, and this is probably the most expensive component in the whole system. So what we basically have here is this transformer. It's a 120 volts AC, another 120 volts AC. These I use in series for a 240 volts AC input. And then it has 240 volts AC out and a 6.3 volts AC out. That is the main component. That's what the whole power supply is based on. So let's look at how that stage gets developed. 30 milliamp maximum on there, 1 amp maximum on here. Okay? So the first thing to do is to add a bit of protection. And how do we do that? Well, a switch So we can switch off our mains and a fuse. We switch on that switch, our mains comes through, there's our live, there's our neutral. Obviously our earth gets connected to the chassis. The first thing to do is let's do an indicator on this switching. So when we switch this on, we want some indication that it's on. The way I like to do that is I put a LED on here. Since this isn't being used for anything, I've got 6.3 volts AC. The peak is probably 9 volts. I can simply use a resistor and a LED. What resistor do I need there? If I've got a peak 6.3 volt AC, it means my peak is 9 volts. I want about 10 milliamps on there. So that's about a 2 volt drop on there. So that'll be 2 volts. That'll be 9 volts peak. So 7 volts across there. To get 10 milliamps, 700 ohms is right. So I use a 680 ohm resistor. So we switch on, our LED comes on. We switch off, our LED goes off. We have an indication. It's protected by a diode, protected by the switch. Nothing else. When that switch is off, nothing switched on over there. Next stage is to rectify this 240 volts. So we take that to a bridge rectifier. That becomes our positive. How much positive do we have on there? Well, we have 240 volts in. The peak rectified voltage will be 240 times 1.414 minus 2 diode drops. So 240 times 1.414 minus 1.4 comes to approximately 338 volts DC. So we have plus 338 volts DC over there. This has a fair amount of ripple. It's just rectified AC. So we need a capacitor to filter that. Put an electrolytic capacitor in here. That will basically do that to the waveform. Rectified and filtered. What rating does this capacitor need to be? Well, we don't need to filter it that much because we're drawing very little current. So I like to use something on hand. And again, what I had on hand is a 47 microfarad. It needs to be fairly high voltage because it will see high voltages across there. So I use a 450 volt cap. We have our B+. It is a fixed B+ at 338 also, depending on how much current we draw. But it is a fixed B+. And how we're going to drop this, we'll take it from this point onwards. Let's have a look how we make this variable quite easily without going into too much complexity in the circuit. Because if you wanted to build a variable high voltage power supply with a lot of precision and very, very high level of filtering, it can be a very, very complex project. I don't want to get into that. This is a simple test piece of equipment. It's a piece of equipment which I will be able to determine the voltage of by looking at that voltmeter that I have across my cap. I can adjust it or want to adjust it to whatever voltage I want across the cap. So it doesn't have to be incredibly ripple-free, it doesn't have to be incredibly stable. However, it has to be fairly high. I can measure up to that leakage. And why is that important to me? Because the reason I'm using these is to measure these caps or to reform these caps. And these all come out of tube radios. That's my main purpose. And tube radios, generally, the ones I've worked on, work up to about 300 volts. Probably less. So I don't really need to worry about testing leakage on capacitors much higher than that. If they're not leaking at the voltage that I'm using it at, it means they're actually good for that voltage. So I don't need to go into something far too complex or more complex than needs to be simply for this tester. Another thing is, if I wanted to test a 1000 volt capacitor, I would need 1000 volts over there. If I have 1000 volts over there, I would need a 1000 volt transformer here. If I have a 1000 volt transformer, I need very high voltage diodes. They're high enough, but I need higher voltage diodes. I would need a very high voltage electrolytic filter cap, which gets very expensive. So I'd probably have to put two in series, piggyback them, and blah, blah, blah. It gets very complex and gets a hell of a lot more expensive. and it also becomes redundant for what I need it for. So this is what my primary supply is based on. Just in summary, a switch, a fuse into the primary, the chassis very well connected to the mains earth in case we have a mishap, which can happen. I have an indicator lamp driven by the 6.3 volt AC heater supply. It's become self-rectified by that half-wave rectified by the diode action, and the limiting resistor is about 680 ohms, so we should get about 10 milliamps or so, 11 milliamps or so coming through this diode. I'll probably actually make this resistor slightly higher because I don't need that much current through the LED. I use the ultra bright. They won't give us the same brightness as if we'd rectified this, because I'm basically getting voltage coming through only on the half waveform. It's rectified half wave through that, but it's good enough. It gives us an indication, and it's cheap and it's quick and it's easy, and the 6.3 volts is available there. I then rectify it with 4 diodes or a bridge. In this case, I've decided to go for 4 diodes. I use 1N4007s. I don't need to worry about putting spike limiters across there because I don't need to worry about having a very, very clean supply. The negative of the supply is connected to our ground of the system. Bear in mind, at the moment, this ground is not connected to chassis, okay? And the reason for that is I want this supply to be floating with respect to earth, for the simple reason that I do want to measure these capacitors halfway in circuit. So I take off one leg, put the ground to there, and I can then just measure or apply the voltage across the capacitor that way, as mentioned in the previous part of the video. I then filter it with this capacitor, and I have my 338 volts DC coming out there. The other thing that I do put in here is a bleeder resistor to ground. And the reason for this is that when I switch off the supply, this capacitor is still charged. No voltage will go back in there because of the diode action, but I will end up with a voltage remaining on here by virtue of the charged capacitor. And that could zap you and could also damage the circuit ahead. So I need this voltage to bleed off to 0 when I switch that off as quickly as possible, not too quickly because otherwise I end up drawing too much current. What I normally use across here is about a 220k 2-watt resistor. If you work it out very quickly, it's about 1.5 milliamp that goes through there. That gets drawn constantly, but because this thing supplies 30 milliamps, that's not a problem. Also, 1.5 milliamp, I squared R gives you the power. You can work it out. This thing will be okay for the amount of charge that this is going to dissipate in the normal working environment. It shouldn't be a problem with a 2-watt resistor. So how do we take the incoming 338 volts DC, fixed DC voltage, and produce a variable 0 to, let's call it 338 for now, volts DC out? How do we create a variable high voltage power supply in here? Well, there are various ways of doing it. The simplest way that I've found is actually using a circuit that's floating around the net and has been for some time, which is used in guitar tube amps to drop the V+ and therefore affect the tone characteristics of the amp. Effectively what happens is your plate voltage gets dropped and your tubes start distorting at different levels, and therefore you change the characteristics of your amp. But it's a fairly generic schematic that's out there, and it uses a Mosfet. And what they do is you take your drain of your Mosfet, you put your incoming voltage into the drain, your output is out of the source of the Mosfet, your gate is then used as to reference the voltage that you want to produce out there. And the way to do that is with a variable resistor, a potentiometer, across here, which is understandably quite high. Normally 1 mega ohm is used. And the reason is you've got 338 volts over there, 1 mega ohm resistor, so you're getting about, 0.3 milliamps? Not enough to heat up this potentiometer. So you won't have a heating problem, a power problem. But what happens then is that this voltage here with the wipe of this resistor, you can vary from 0 up to the maximum of 338. Now what you do is you feed this to the gate, not directly. What you need to do is, this is an N-channel Mosfet, by the way, and there are various specs that we need to go through, and I'll explain what we need to be careful of over there. What you need to do is you need to ensure that you don't have overvoltage across this junction over there. So you need a resistor in there, 100K does the job, and you need to ensure that this gate to source voltage never exceeds the breakdown voltage of this of the Mosfet. So a Zener diode is used over here. Use a 12-volt Zener. What this means is that the voltage between the gate and the source will never exceed 12 volts. And you put in a current limiting resistor there of 10 ohms. And I'll show you exactly what happens over here and why this thing works, and also what the drawbacks are. So firstly, when you have this thing unconnected, you have 0 volts over there, you have 338 over here. Let us assume you take this to about a third. Let's say you got 100 volts over there. This N-channel Mosfet has a threshold voltage of about, I believe it's about 4 or 5 volts. And what happens is that this is at 0 volts, that is effectively at 12 volts, so you have a current going through there, which is getting dissipated through the Zener, which is 100 volts minus 12 volts divided by 100K. So it's, 0.8 milliamps or so, or less, because you then got that resistor as well. So current starts to flow. When the current starts to flow, this voltage starts increasing. As this voltage increases, this difference starts decreasing. As this difference starts decreasing, the FET closes down. So you end up with a dynamic situation here where this MOSFET will effectively follow minus a couple of volts the voltage that you have on here. The MOSFET itself doesn't take any current. So it's not a question of supplying current to the gate of the MOSFET. It's a voltage controlled resistor effectively. But you do control the voltage that comes out here because it will follow minus a couple of volts drop, a few volts drop, the voltage that you have on here. And this works perfectly. There are a few drawbacks. One is, let's say, for example, you set this so you end up with 50 volts out there. You have 50 volts there, which effectively is practically the same at the source, and you have 338 over here. So you've got 288 volts across this MOSFET. Multiply that by the current going through it, and you find that the power dissipation here can be quite high. So you need a MOSFET that is built for high power dissipation, and you need a very, very good heat sink on there as well. So that's the first consideration, heat. It's a problem. You need to make sure that that is properly connected to heatsink so that you don't burn out this device. The other thing you have is, if this thing is at 0 volts, if you set this down to 0 and you've got practically 0 volts over there, you end up with a voltage across the drain and source which is the entire 338 volts, which means that you need to make sure that this junction, these two parts of the MOSFET can withstand that kind of voltage. So you need a high voltage MOSFET. Okay? And the other thing is the breakdown voltage, the threshold voltage of this particular MOSFET is also affected. And one of the reasons you have to be careful that you don't forget this resistor in there. This resistor helps to work as a negative feedback within this loop over here, so that as the current increases, the voltage across there increases as well, which means that the source voltage gets higher with relation to that, so the gate to source voltage drops, therefore the MOSFET closes, reduces the current, that voltage drops again, and it stabilizes that way. Now, this thing works with quite a lot of MOSFETs. One thing you've got to be careful with is not to put in a filter capacitor at this end. One would think that you'd need one. It makes sense. You could put in a 10 microfarad or so. It would smooth out this voltage, whatever voltage you've set with your pot. However, it also creates a problem that when you drop this voltage, this one will be higher than that one, and you'll end up with conduction through this diode, and you mess up the whole biasing system of your Mosfet, and you could have some catastrophic results. Now, the Mosfet that I use is a IRF P27N60K. Now, you can use a lot of different Mosfets. This denotes 600 volts. It's an N-channel Mosfet. If you use a P-channel, this won't work because the P-channel needs a negative voltage, or rather the gate has to be negative in relation to source. In this case, our gate has to be positive in relation to source to start conduction through the Mosfet and reduce its resistance. So this system works, and what I end up here is my V+, which my capacitor wants to see, and it is variable with this pot. From 0 to the maximum there is a few volts dropped between this stage and that stage, which is fine for two reasons. One, there actually is a voltage drop across the drain to source. Even when it's fully on, it has, I think it's 180 milliohm on resistance if it's fully on. This thing is working in the intermediate stage, so it's not ever fully on. The other thing is that you have current going through there. The more current you have through there, the higher the voltage drop, so the lower the voltage you'll get on there. However, because we're adjusting this pot based on what we see on that voltmeter that we have across the cap, remember, we are basically adjusting this voltmeter visually by moving the pot. And we can adjust it to whatever we want. And obviously, depending on the leakage, more current will flow, so the voltage will drop, but you are adjusting it. You are the feedback system in this circuit. And this is not something you want to play with by leaving it there. You need to be on hand. You need to play with this on hand. So you'll always be adjusting the voltage over there. And it drops fairly quickly because when you reduce the voltage here, or rather when you turn your pot counterclockwise, you're reducing the reference, and therefore the output will drop as well. Again, the power across here increases, but if your current is low, it shouldn't be a problem, especially if you have the adequate heat sinking on there. The other problem we have, or the other challenge, is the actual voltage across this pot. Now, in this condition, I have 338 volts across this potentiometer. Now, most pots are built for, I believe, 250 or so. So I am exceeding this, and it could, in fact, be dangerous. I have had no problem with this. I've used it in the scaling systems of guitar amps before as recommended, and I've never had a problem, but I do use some pretty chunky pots over here. I certainly wouldn't go for a 9mm or a 16mm pot. I use the 25mm pots, and I make sure that it's a good quality pot so that I don't end up with a breakdown because of the voltage across it. And also, this pot has a metal body. It is connected to the chassis. The chassis is connected to the mains earth, as I indicated in the previous part of the video. So if there is some catastrophe, it goes straight to earth, and it should protect you a bit more than if this thing was not connected to the actual chassis. So you want to make sure that the metal chassis, the metal part of the pot, is actually touching and bolted to the metal chassis of your entire system. So here's our variable voltage system, our variable voltage regulator effectively, which we then end up with producing our variable voltage to apply across the cap. Now, so far so good. So you have your variable voltage, you have your B+, fairly smooth, you have your variable voltage, you can adjust it, and it's all hunky-dory. Now you put it across your cap, and depending on what meter you use, the voltage could be fine because you make sure that your meter, your voltmeter can read up to 338 volts or 400 volts or whatever it is. But now you find that your ammeter is reading 0. And why is that? Because you might have a 1 amp ammeter on there, or an ammeter rated for 5 amps, or an ammeter rated for 100 milliamps. Now, the leakage current is actually fairly low. It should be very, very, very low. It should be microamps. if that. So you need to use a very sensitive ammeter. However, if you put in a 100 microamp ammeter, which is quite common, quite easy to find, and when you switch this thing on, you find you have a very, very high leakage on a capacitor, your ammeter will peg and probably burn out. Or if you have a short on that capacitor, it'll peg and burn out. Or if you use an electrolytic and the initial surge current is very high, it'll peg and burn out. So you end up with a balance that you have to achieve between being able to read down to very, very low currents and not burning this thing out when you initially switch this on, because you don't really know what current draw initially you're going to find. Now, as you will see, we take this V+, we're actually going to minimize the maximum current. We're going to assume that there's a short on here, and let's assume if this is shorted to ground, what do we need to do to reduce this current? A, to protect our Mosfet, B, to protect our transformer, and C, to protect any measuring equipment we have in between. Well, the thing to do is to define the maximum current that we have coming out of the transformer is approximately 30 milliamps. So what we need to do is ensure that we get a maximum of 30 milliamps. So the way to do that is to put in a resistor in here. Now this R should allow maximum 30 milliamps, assuming a short and assuming we have this on max. So let's call this 330 volts instead of 338, 330 volts. The resistor needs to reduce the current to about 30 milliamps. So what we end up with is 330 volts over 0.03, right? So that comes to approximately 11K. I use a 12K 2 watt. I use a 12K 2 watt resistor in series coming out of there before it gets to any usable V+, before it even sees any part of the measuring circuit. So if I do short it out, I end up with a maximum of 30 milliamps through here. And I've protected the system somewhat. Obviously, if this stays on there for very long, I'm going to have a problem because this will heat up and the transformer will be supplying its maximum voltage, maximum current. That's not a good thing. But at least I'll be able to see that on my meters because, as I said, you are there, you're doing it on the spot. And you can then reduce the voltage immediately or switch off the system because you know you have a short to ground, or you have an incredibly high leakage on your capacitor, which is practically the same as a short to ground. So our 12K resistor reduces that. Now you say, okay, well, a 12K resistor in series here will mess up my voltage over here. Well, yeah, it will. If the current is high, if the current is 1 milliamps, I'm going to get a 12 volt drop. If it's 10 milliamps, I'm going to get 120 volt drop. Now that's not going to be very useful, but look, I'm trying to measure leakage, and I'm trying to measure very low leakage. So if I have a 10 milliamp current and I have a 120 volt drop, I will see that straight away because I'll have to push this thing up and I'll find that that thing is very, very low. So I'll know that I have a short. I'll see that on my current reading and I'll be able to then take measures to get rid of that voltage, take it down or switch it off. So I put this in as a protection. Now, under normal circumstances, if I have a 1 milliamp leakage or a 1 milliamp current which is being used to reform one of my electrolytics, I have a 12 volt drop. Well, 12 volts on a scale of 330 isn't a big deal. I'm adjusting this to the voltage that I see there anyway. So I can compensate for that. And that thing is then negligible in the scheme of things. And it does serve the purpose of protecting the entire circuit. 2 watts, why? Because if I have, 30 milliamps going through it, 30 milliamps squared times 12K, I can't tell you off the top of my head what that comes to, but it probably is less than 2 watts. And anyway, that'll happen for a very short time, so you can take measures to reduce it right away. But it's safe enough under those conditions. So here we have our voltage regulation circuit. We have our V+. Now, we go back to the first schematic with the capacitor, with the ammeter and voltmeter, and we have to see how we switch something in to calibrate, or rather to create various ranges on our ammeter reading. We don't need to worry about getting ranges on our voltmeter, because we don't really care if it's 50 volts or 51 volts or 52 volts. It's close enough. If you have a voltmeter that reads up to 400 volts DC, you're fine. You can see it on the scale. As long as it's fairly accurate, you're fine. If you have an ammeter that measures 100 microamps, which is the one that I have, I need to make sure that I can read, 30 milliamps, that I can read 10 milliamps, that I can read 1 milliamp, but I also want to make sure that I can read 100 microamps, up to 100 microamps. I would like to be reading somewhere in the 1 or 2 microamps every time I put a capacitor in here. That's utopia. That means my caps aren't really leaking, but it's not going to happen. There are going to be cases where the readings are high and I need to know, or I want to know, how high they are. So I need to switch in various ranges, and we'll look next at how that is done. Okay?